Swayam Prabha. Digital India. Educated India.
Good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. We have actually been through a lot. Today's lecture is lecture 36. So we basically have done about 90% of the lectures. So we've covered a lot of ground and we are currently in module 4. So module 1 was an introduction. In the introduction, I tried to tell you what are the different types of rigid pavements: JPCP, JRCP, CRCP, PCP. And particularly, I told you for this class, we're going to be mainly talking about JPCP, that is the vast majority of rigid pavements. But the CRCP analysis tends to go strongly along with JPCP until the point of design where there's a slight deviation between the two. And indeed, in Indian practice, there's actually no deviation at all. We'll talk about that later. But largely, to a large extent, when we're studying CRCP, when we're studying JPCP, we are also more or less studying CRCP at the same time. JRCP, very rarely used, and that's why we're not going to talk about it. PCP is a very specialized application, pre-stressed concrete pavements, and so they are best studied actually in the context of structural engineering at this point, not within transportation engineering or pavement engineering. Now, we looked at several lectures on analysis of rigid pavements. In the analysis of rigid pavements, we started out with the classical methods, Westergaard's theory and Freiberg's methods and various updated versions of that. Currently, what we're doing in module 4 is we are talking about the mechanistic empirical design of rigid pavements in the Indian practice. And the Indian practice uses the code of design, which is IRC 58. Now, what I went through a couple of lectures ago, I went through a brief history of IRC 58. You saw it essentially started around in the 1950s. So the first edition when it first came out was somewhere in the 1970s, I'm sorry, not 50s. It came out somewhere at that point when rigid pavement construction was picking up in India. And it started actually using stress calculations based on Westergaard's theory. And it was also using Bradbury's coefficient, so Bradbury's theory, to account for temperature distributions or curling stresses. The key aspect of Bradbury's theory is that the loading and the temperature distributions are decoupled from each other. That is, according to Bradbury's theory, the assumption built in that for a JPCP section, when you have a temperature distribution, that is, when you have some type of a curling behavior, you're going to get stress even if you don't have an external load. As we had talked about then, that when you have a temperature distribution, that is, the pavement tends to take this kind of a shape. That's a very critical term I keep using. It tends to take the kind of shape. On its own, without any sort of external restraint, the restraint being, for example, a load or self-weight. On its own, no stress is developed. So without any external load, this shape that the pavement tries to tend to take, it will take, and therefore it's free to assume this shape and there is no stress. Stresses are only developed when there's some kind of something to prevent or some kind of restriction to this type of strain which is being developed. So in those old classical methods, Westergaard's theory and Bradbury's equations, etc., the assumption was basically that the stress is purely based on the temperature stresses, the curling stresses depend just on the temperature and not on the load. It has been understood for a long time that this is not correct, and that the load and the curling stresses, at least, there is eigenstress, which is a different component, which doesn't depend on the load, but at least the curling stress component, which is a very large component, that certainly depends on the magnitude of the external load as well. So subsequent versions of IRC 58, but including IRC 2015, which is going to be a topic of discussion today, subsequent versions have taken this into account. How have they taken this into account? Using analytical methods, which we learned, it's actually very difficult to take the joint effect of temperature and of temperature distribution and loading into account. But we do not actually use these classical methods anymore. So whether it's the AASHTO MEPDG or it's IRC 58, these classical methods are not really used anymore. I taught it to you mainly for historical reasons, also to get a little bit sense of what the magnitude of the numbers look like, how much stress can you expect, what is the stress ratio can you expect. But in practice, what we use in modern theory or modern design practices, most parts of the world, is using finite element method. So the finite element method is a numerical method. Without going into all of the details, I just want to remind you that in the finite element method, we take a differential equation, partial ordinary differential equation, and we turn it using a variety of techniques. We convert it into a series, a very large number of linear equations. So the reason it's a very large number is we don't actually solve 2 or 3. We actually have to discretize our domain, our slab, into a series of points, and then at each point we're going to solve a couple of equations corresponding to the number of degrees of freedom or the number of unknowns that we have. So we're not talking about 2 or 3 equations. Generally, for a typical finite element problem, we will have thousands, tens of thousands, lakhs of degrees of freedom, and therefore we're going to have that very large number of equations. Naturally, we don't solve it by hand. There are very good, sophisticated, commercial as well as open source computer programs which can be used today, which can take care of these calculations for us. So it's no longer necessary for us to explicitly do all these calculations ourselves. Now, in ASHTO, when we had in module 4, when we started learning about ME design, as I keep mentioning, that the reason we learned analysis before design is in mechanistic empirical design, and the design process is an iterative analysis process. That is, we start from trial section. We have to perform an analysis. From that analysis, we have to calculate a structural response, which in this context basically just means stresses, or sometimes it can mean deflections if you're looking at faulting. Generally, strains are not an issue in JPCP. Strains become an issue in flexible pavements, but since we're talking about rigid pavements, it's mainly what we're interested in is stresses and sometimes deflections if we're interested in faulting. So we calculate stresses, and then using fatigue theory, those are SN curves, we can calculate the fatigue damage. That's the mechanistic part of the design. The empirical part of the design is we take the fatigue damage and we convert it to some amount of distress. Could be cracking, could be faulting, could be punch outs, etc. We convert it into some distress, and then we compare that distress along with some reliability factor included. We compare that distress to what is the acceptable level of distress. Are we okay with 10% cracking, 20% cracking, 30% cracking, 5% cracking? That's a policy decision. We compare the calculated value to the policy recommended maximum value. If the distresses which are predicted are more than what is allowed by policy, then that's a failed design. We have to then go back and update the design, which itself is quite a process itself. So design optimization is quite a process itself, and we had a complete lecture dedicated to design optimization in a couple of lectures ago. Please go back and review that. So we go and update and try to optimize the design until we get an expected distress less than the maximum allowable distress. Once we get that, we say that that is our final design, and we accept that as our final design. So as you can see in this whole process, calculating the stresses is very, very critical. In a mechanistic empirical framework, it is very important that we know how to calculate stresses for our slab. Again, you have a variety of different inputs. You have the properties of the slab, you have the thickness of the slab, you have the layers below the slab, you have the subgrade itself, which is characterized by a K value. Then you also have consideration, for example, of loading, temperature. There's a large number of considerations that we have to take into account in calculating stresses. So in modern theory, we do use the finite element method to do these calculations. So in ASHTO MEPDG, I first gave you an overview of what is the finite element method, and particularly I also gave you an introduction to a program called iSlab, which is part of the calculations in MEPDG. But one of the lectures we talked about that we don't actually do the calculations through using iSlab. Instead, what they did is they actually developed a series of neural networks. There were 4 different neural networks which were developed, which automatically do these calculations, but they do it about 1,000 times or more faster than actually solving the finite element method. So it's very, very fast methods which were developed to do these calculations, because since design is iterative and you have to do a very large number of calculations, there was a need to come up with a relatively fast method to do these calculations. Always expecting a designer to run a finite element program again and again is an unreasonable expectation. It just slows down the design tremendously. So in the ASHTO MEPDG, they did develop these neural network predictive models. It's some kind of a statistical, or you can say a non-parametric regression model, which was developed in order to calculate stresses instead of full-fledged resolving the finite element problem. We also saw, interestingly, that in the ASHTO MEPDG, dowels can be considered together with the slab. So we looked at something called the component dowel bar model, but what basically happens is the stiffness matrix. So at the end of the day, in a finite element method, we get a stiffness matrix which contains all our physics. We just include the physics of the dowel bars between multiple slabs into the stiffness matrix. Please go back to that corresponding lecture. That was probably the most technical lecture that we had. Please go back to the lecture if you want a review on the component dowel bar model and how you can actually include the effects of dowel bar in the overall stiffness matrix of the entire system. It's actually quite an interesting thing that can be done using the finite element method. Anyway, that was all on MEPDG and how to calculate stresses using MEPDG. So I hope now you have a clear idea that in the MEPDG, there is a very sophisticated model that calculates stresses. It is so sophisticated, in fact, that you do need the corresponding software. So the companion software, which is Ashtoware Pavement ME, it is necessary to use that software if you want to do these calculations. They're too complicated to do by hand. Now, in what we've been talking about for the last couple of lectures is moving away from ASHTO MEPDG. We've been talking about IRC 58, so the Indian practice. In particular, we're looking at IRC 58 2015, which is the fourth revision or the fifth edition of the manual. So over time, I showed you in an earlier lecture the history of IRC 58 and what are the different updates that have been happening over time. And currently what we saw is that around in 2000, roughly in late 2000s, a very big change happened in IRC 58. That is, up to roughly the early 2000s, IRC 58 was using Westergaard's theory and Bradbury's equations for stress calculation and curling considerations respectively. We already saw that there are several problems in using Westergaard's theory, particularly the assumption of a very large slab can lead to very significant overestimation of the stresses, and then the complete decoupling between loading and curling stresses is actually not correct. From physics perspective itself, it's not actually correct. So that's why roughly in the late 2000s, new models, which is based on a program which is called IIT SLAB, which was developed at IIT Kharagpur, those new numerical models were developed and updates were done to the stress calculations in IRC 58. Today's lecture, which is lecture 36 in our overall course, we're actually around 90% done so far. So in today's lecture, we are going to look at those very models. Critical stress prediction in IRC 58. How are these critical stress calculated? That's going to be the subject of today's lecture. So the aim of today's lecture is I'm going to explain what are the critical loading conditions. So remember, when you're looking at a finite element model, your stresses which are developed, of course, I already mentioned they depend on the material, they depend on the thickness, etc. But they also depend on where you put the load. Depending on the position of your load, you can develop different stresses. So it's not just important to understand how to calculate stresses. It's also important to understand from a design perspective, where should you put the loading such that you're going to get the maximum stresses. And that's what we call critical loading conditions. So in today's lecture, I'm going to look at critical loading conditions. And then I'm going to show you, after looking at critical loading conditions, I'm going to show you how stresses are calculated. We'll actually do an example. I'll show you, the example actually we'll do in the next lecture, but I'll show you this critical stress calculation model in IRC 58. Okay. So just as a reminder, when we are trying to calculate stresses in any problem, it's not necessarily only on JPCB, but in any problem when we are trying to calculate stresses, we are basically doing it based on the assumption that our structure, in this case the slab, our structure is behaving according to some law. The general law that we've seen that has been used historically for JPCP sections is the Sophie-Germain equation. We've seen this equation before. This is the equation for a medium thick plate, and if you additionally add the effect of a Winkler foundation, you get this KW term over here. So we already saw the derivation of this. We've seen how this can be used in the finite element method. I'm not going to repeat it. You want to go back to module 2 and module 3, where a significant amount of time was devoted to just this particular equation. So it is possible then, if you want to analyze the behavior of a slab, we could start from this equation. But there is actually a more general way to do it. That the only way to analyze the JPCP is not this equation. You could do it with this equation, and there are benefits to doing it with this equation, but it's not the only way to do it. It can also be modeled using something called general continuum mechanics. So there is a class of methods, a class of theory called continuum mechanics, and within continuum mechanics, you can basically have a general continuum mechanics which can define any elastic solid body. So whether you're analyzing a JPCP slab, or you're analyzing a column, or you're analyzing a beam, etc., all of these can fundamentally be analyzed using a common theory, which is general continuum mechanics, of course with some errors involved. And that basically the governing equation of that is this equation, del dot sigma is equal to 0, which is the divergence of the stress tensor. Stress is a tensor. So the divergence of the stress tensor at any point is 0. Of course, this is for static conditions. And this is also when you do not have any body forces. So no body forces. So this equation is then valid for that. Again, I assume most of you have a civil engineering background. Maybe you've seen this. I hope certainly you've heard of stresses and you know what that stress is a tensor, and I hope you know what a tensor is. Maybe some of you have seen this particular equation. Maybe some of you need to take a little bit more advanced class. It's not very important for this class. I'm just telling you that you could solve a slab or actually any structure using this general equation. That's one approach to the finite element method. Another approach to the finite element method is what we say is we add additional conditions which are called kinematic conditions. And for a medium thick plate theory, the kinematic condition, if you go back to that lecture, was that shear stresses or shear deformations are not admitted. So a section which is plane before bending remains plane after bending. That was a very, very important assumption. If you go back to that lecture, I put a lot of emphasis on that assumption. If you make that assumption, then you can actually derive the Sophie-Germain equation. If you don't make that assumption, you can still analyze JPCP using this equation, del dot sigma is equal to 0. The problem is you are still going to get some more errors. In this case, you will actually see some amount of transverse shear is occurring, and you have to have a very, very fine mesh in order to minimize that transverse shear. So that's two different ways of using a finite element method. It's not very important to understand the details at this point, but I just want to show there are alternative ways to do these analyses. Okay. I also wanted to talk a little bit about loading conditions. So remember, when we apply a load on the slab, we are going to get stresses. Stresses are going to be obtained at every point. In particular, if you are doing the stress calculation using the finite element method, at every node we are going to get some amount of stresses. We are not interested in all the stresses. We are interested in the critical stresses that lead to the highest amount of tension, because concrete is much weaker in tension than in compression. The tensile strength of concrete is 4 to 5 megapascals, whereas the compressive strength is at least 10 times of that, if not more, typically as it's used for concrete. So generally our failure, except for dowels, our failure mechanism is going to be in tension. So we are actually interested in the loading configuration that gives us the highest possible amount of tension in the slab, because it's that tensile stress then where we expect failure to happen, where we expect cracks to start propagating. The loading conditions actually come from a relatively small condition of load configuration of each axle type. And we have seen this in previous slides. We had something called a single axle, a tandem axle, and a tridem axle. Just to jog your memory, so an axle, basically it consists of a shaft, and on the shaft we can have a wheel. We could have an axle with single wheel on either side, so that's called a single wheel axle. More likely for trucks of a heavier vehicles, which we are generally concerned about, we can have this dual wheel type of configuration. So we can have an axle which is the shaft, and we can have either a single wheel or dual wheel, but generally dual wheel is what we are concerned about for most trucks. We could have just this one axle, and it's possible the next axle on the truck is significantly far away, so that these two don't have to be considered together. However, for historical reasons, if the distance between two adjacent axles is less than 1.8 meters, this is Indian practice, if it's less than 1.8 meters, then we actually consider them as a common axle group, and that's called a tandem axle. Similarly, if the third axle is such that the overall outer distance is less than 3 meters, again Indian practice, if the overall outer distance is less than 3 meters, then we call that a tridem axle. So we can have single axle, we can have tandem axle, and we can have tridem axles, and we can individually have either single wheel or dual wheel, although in most cases we tend to have dual wheel in all cases over here. So depending on the size and shape of the slab, that is the thickness of the slab and the geometry of the slab, depending on what type of axle configuration we have, and depending on where we place the axle on the slab relative to the joint, because the joint is the very critical issue over here. Depending on these three conditions, we can have different stresses which develop. The question for us as designers is, which condition should we use? What size of slab should we use in our design? Where should we place our, of course the thickness is something we have to design for, so that's really something that we have to iterate over, that's not a final answer. But size of the slab is something that as a designer we have to choose. What is the axles loading and the number of axles we have, that's also some input we get from traffic considerations. But where do we put the axle? Do we put the axle exactly at the edge? Do we put it some distance from the edge? How much distance from the edge in that case? If we have to consider wander, recall in MEPDG lecture, we did talk about wander. The fact that the mean wheel path is actually not at the edge, and the mean wheel path, the actual wheel path does vary around the mean wheel path. We looked at those concepts in the MEPDG lecture. Please review that again if you need a reminder. But it tells you that as a designer, we have to choose where do we put the load relative to the edge. That then leads us to the question of what are the critical loading conditions. Separately, IRC 58, besides talking about critical, so I'll tell you the answer for the question in a second, what are the critical loading conditions. But IRC 58, besides the critical loading conditions, it also takes into account, like MEPDG, that you have separate considerations for bottom-up cracking and separate considerations for top-down cracking. So when you have bottom up cracking, then bottom up cracking, which is this figure over here, this basically happens when delta, sorry, this is bottom up cracking, this basically happens when delta TL is greater than 0. That is again, delta TL is always by definition is top temperature minus bottom temperature. That is the definition. So it's not bottom minus top, it's always top minus bottom. So delta TL is top temperature minus bottom temperature, and in that case, that means the top surface is relatively warmer than the bottom surface. So the top surface is going to expand and the bottom surface is going to relatively contract, and so it assumes this type of a shape which is curling upwards. In this type of situation, if this is the reference, if this is the configuration of the slab, then the critical loading occurs when you place a wheel, exactly at the middle of the slab. In that case, a tensile stress is going to develop at the bottom of the slab, and that's why this is called bottom up cracking. So this tensile stress will develop at the bottom, a crack will initiate at the bottom and will start propagating upwards. So it's going to propagate bottom up and hence bottom up cracking. That's one condition. The other condition, that is, if you have delta TL less than 0, then this is a situation of what we call top down cracking. In top down cracking, here the top surface is relatively cooler than the bottom surface. So the bottom surface is going to relatively expand and the top surface is going to relatively contract. And so you take this type of shape. In this case, if the load is actually applied in the middle, very little stress is actually generated. A high stress is generated when the load is going to be applied at the ends. Now, it doesn't have to be applied exactly at the ends, it could be applied a little bit closer. But certainly, if the two wheels are so far apart that one wheel is on the slab, but the other wheel is off the slab, then that's a completely different type of condition. So you get critical stresses for top-down cracking when you have the loads which are exactly placed at the ends of the slab. And in this case, the tensile stress is going to develop at the top of the slab. When the tensile stress develops at the top of the slab, that means cracking is going to initiate at the top of the slab. It initiates at the top and then it starts propagating downwards, hence the name top-down cracking. So the IRC 58 recognizes both bottom-up and top-down cracking, and it recommends for each of them certain critical loading conditions. What are those critical loading conditions? They are as I show in this figure over here. So for bottom-up cracking, the stresses can be calculated, the critical stresses, I should add here, the critical tensile stress can be calculated either with a tied or an untied shoulder. So tied and untied shoulder, we had discussed a bit in the MEPDG part of it. So when you have a tied shoulder, that basically means you have a concrete shoulder and there are tie bars in between the lane and the shoulder, and therefore there's some amount of stress redistribution which is occurring, that the shoulder is bearing some amount of the stresses which is away from the travel lanes. You also could have untied shoulders, which could mean you have no shoulders, or they are flexible pavement shoulders. In that case, you basically do not have that load transfer. So the travel lane has to bear the entire load. So either case, whether you have a tied shoulder or an untied shoulder, IRC 58 tells that you can still calculate for both of them the critical stresses. And the critical stresses can be analyzed for bottom-up cracking for these loading configurations. So let's look at the loading configurations. If you have a single axle, again, mostly we always assume dual wheel in this case. So single wheel is sometimes used. We'll see single use actually when we get to top-down cracking. But on critical conditions where loads are being placed on very heavy trucks, generally we'll always have dual wheels. So if we have a single axle dual wheel, then the assumption is as follows. The tire has to be the leftmost tire is generally placed at exactly the edge, exactly at the longitudinal edge. And then it is placed transversely, transversely it's going to be placed at exactly the middle. So it's placed along the longitudinal edge, and transversely it's placed exactly along the middle of the slab. And in that case, then the critical stress will occur at this point, which I've just highlighted over here. It's going to occur just outside the outer wheel. So if I actually draw this in a different way, here, for example, if I have my longitudinal joint, so this is my longitudinal joint, the critical loading conditions recommended by IRC 58 for single axle dual wheel is put one wheel exactly over here, the next wheel is here, and then the other wheels are on the other side. This is the critical loading conditions recommended. In that case, it says the maximum stress for bottom up conditions is going to occur exactly over here, exactly at the edge is where you're going to get the maximum stresses. If you have tandem axles, then similarly in tandem axles, it is recommended that it is placed in such a way that you actually place that the center, that transversely the center is placed along the center line of the axle, and the maximum stress is going to, critical stress is going to occur at this point just below the wheel. Again, still it's placed exactly at the longitudinal edge. And if you have a tridem, then for tridem, the recommendation is that the middle tridem wheel, so the tridem axle consists of 3 axles, the middle axle has to be placed exactly at the center of the slab longitudinally, and the entire axle system has to be placed along the longitudinal edge thus. Okay, so these 3 then give us what are the critical loading conditions for bottom-up cracking. There is an additional note which is provided, which I am going to just read out to you. The note is as follows: tire imprints are tangential to the longitudinal edge, which is the same thing I said. The tire imprint has to be placed exactly at the longitudinal edge. Okay. For tight concrete shoulders also, the maximum stresses occur in the same location. So these maximum stress locations which are shown, regardless of whether it's tied or untied, we still calculate the same. Obviously, the actual magnitude of the stress is going to be lower if you have a tight concrete shoulder compared to if you have an untied shoulder, because when you have the tight shoulder, then the shoulder is taking away or it's transferring some amount of load from the main lane, the travel lane, to the shoulder. So you'll have a lower stress. We'll see that calculation a little bit later. Okay. Single axles cause the highest stresses, followed by tandem and tridem axles respectively. That might seem a little bit counterintuitive, that you would, if you actually look at the axle load spectrum. So if you go back to our lecture on traffic characterization and you look at axle load spectrum, you'll see that in axle load spectrum, the overall load of a tandem axle is actually higher than the overall load of a single axle, and tridem is higher than the tandem. So you would think because tandem axles are heavier than single axles, tandem axles should be causing more stress. But actually what happens is they're not proportionately heavier. That is, although tandem axles overall are heavier than single axles, but they also have more tires. They actually have double the number of wheels, double the number of tires. So the load which is actually taken by each tire also decreases, and decreases disproportionately. In general, what has been observed is the load per tire is highest for single axles. It's just that the number of tires is fewer. And the load per tire actually is less for tandem and even less than that for tridem. So the load per tire is less, but because we have more tires, the overall load of the axle increases. But the stress as such depends only on the load of the tire and the relative configuration of the tires. And that's why the single axles cause the highest stresses, followed by tandem and tridem axles respectively. All right. Spacing between individual axles, it has been seen the spacing between individual axles for tandem and tridem varies from 1.3 to about 1.4 meters. I had already pointed out to you that the upper limit for calling 2 axes as tridem axles in the tandem axles in the Indian practice is 1.8 meters, and 3 axles, the upper limit for calling them as tridem axles is that the overall outer spacing should be no more than 3 meters. That means on average, the spacing between the individual tires should be no more than 1.5 meters, or at least the minimum spacing should be no more than 1.5 meters. And so 1.3 to 1.4 is both within that range. There's practically no difference in stresses for axle spacing between 1.3 and 1.4. That's relatively true. It's a relatively small difference, so you don't get too much of a difference in the stresses. So it is generally assumed in these calculations, a spacing of 1.3 meters has been used in these guidelines for stress computations. So that means it's assumed that the spacing between the axles for tandem axles as well as for tridem axles, it's assumed to be 1.3 meters, although the upper limit is actually higher than that, but that's the assumption which has been made over here. So this is the critical loading condition for bottom-up cracking. Namely, we always consider dual wheels in this case. For single axle, for tandem axle and for tridem axle, generally we try to make it symmetric about the center line, in the center line transversely. So we try to put it exactly at the longitudinal edge and at the center of the longitudinal edge. And we assume that the spacing between the tires is 1.3 meters. In that case, the critical stress at the bottom of the slab is going to occur exactly under the outermost exactly under the wheel, which is just parallel or just next to the longitudinal joint. Okay, so that is for bottom-up cracking. Now let's look at what we do for top-down cracking. Top-down cracking, again similarly, you can do it. We have the capability to do it for both tied as well as untied shoulders. So in both cases, the analysis has been done for both tied and untied shoulders. Now for top-down cracking, it's a little bit more interesting. Keep in mind, for top-down cracking, what we need in our critical condition, which I showed previously, if you have this type of a condition, ideally you need a load over here at one side of the slab and you need a load at the other side of the slab. If you have this configuration, that a load is kept on one side of the slab and on the other side of the slab, that is when you get the maximum amount of tensile stress which is developed over here. And so our critical loading conditions has to correspond to this. Now, generally the width of a slab is going to be 3.5 to 4.5 meters. Indeed, in IRC 58, the assumption is that in the longitudinal direction, the width is actually 4.5. And in the transverse direction, the width is 3.5. So now, what happens then is now 4.5, if it's 4.5, that's a pretty wide base. It's generally not, and the overall outer limit for a tridem axle is simply going to be 3 meters. So that means if we want that these two wheels need to be part of the same axle group, that they need to be part of the same tandem axle, the same tridem axle group, then their overall spacing should be 4.5 meters. That's too high. If you have a spacing of 4.5, you are neither a tandem axle nor a tridem axle, it's just a single axle, generally an unrealistic sort of configuration. So then so does that mean we don't have to bother? We don't actually get any stresses, because if we can never get this type of a configuration such that the wheels of the tandem and tridem group are 4.5 meters apart, does that mean we never have to consider top-down stresses? No. In this case, we actually have another type of axle, which we generally, and I talked about this in an early lecture, we can call it the front axle, or we can call it the steering axle. Keep in mind then the truck. So if I had to draw a truck overall, we might have, and I've shown this diagram before. This might be what a truck looks like, very sort of cartoonish way to draw it. We have this front axles over here. Then we might have more axles. We might have a tandem axle sort of thing over here. This is a very typical sort of truck configuration which we have. We can have more axles also. But this is a particular situation that we can have. In this case, what we see is we have this front axle, which is called which is also called the steering axle. Generally, it's the axle without any power. Unless you have an all-wheel drive configuration, it's the engine is not actually providing any power to the front axle. The power is provided to the rear axles. The front axle can move around. And so the front axle is actually what's used to drive and make turns. The rear axle is what powers the vehicle forward. So furthermore, the front axle generally is not taking much load. The rear axles have to bear whatever load is stored inside the truck. The front axles have to bear the basic chassis of the truck, they have to bear the load of the engine, and they have to bear the load of the driver and their personal belongings. That's not much load. Compared to the overall amount of load carried in the truck, those things are relatively small, of which the engine is the vast majority. It's not too much. So generally, I had mentioned for bottom-up cracking, we always have a dual wheel configuration. Indeed, for all rear wheel axles, because we have a very large number of a very heavy load, generally for rear axles, we always have dual wheel configurations. But because the front axle is bearing a significantly smaller load, it is not always necessary to have a dual wheel configuration. What is common and what is used in IRC 58 as an assumption is that the front or steering axle is actually single wheel and is also single axle. So it is assumed that the truck consists of a front axle, which is a single axle, single wheel SASW configuration of a certain specified load. All right, so that's what we see over here. We assume that the front axle is single axle, single wheel. Now the rear axle, that is always dual wheel, and that can be single axle, tandem axle, or tridem axle, because the rear axle, as I showed over here, that is what's actually holding up the bulk of the load. So that can have a variety of different configurations. So the critical loading configuration, according to IRC 58 for top-down cracking, are the front axle is placed at one transverse joint. So the front SASW steering axle, that is placed at the one transverse joint. 4.5 meters behind it, to the next transverse joint, you place the first set of axles of the rear axles. So, for example, if a rear axle is a single axle dual wheel, then you place that single axle dual wheel on this transverse edge. So, the front axle is placed on this transverse edge. 4.5 meters from that, the single axle is placed on the other transverse edge. And of course, both are placed such that the outer wheel of the rear axle is just at the longitudinal edge. That is the critical loading condition assumed in IRC 58 when the rear axle is single axle dual wheel. So if our rear axle is a tandem axle, then our critical loading condition is as follows. Again, the steering axle we continue to place at the front transverse edge, the front transverse joint. The rear axle, the tandem axle, and this is where it gets interesting, we assume that the first axle in the tandem axle is also placed on the same slab on the transverse edge. And then we assume the second axle in the tandem axle is actually on the next slab. Now keep in mind, when it's on the next slab, it doesn't mean we don't have to consider it. because the slabs in this direction do have dowel bars. So there is some amount of load transfer happening. So you can't ignore the effect of it just because it's on a different slab. But that is our our critical condition, that you have on this transverse edge, you put the first wheel of the tandem axle. Behind it on the previous slab, you put the second wheel. And the front transverse joint contains the front or steering axle. In the transverse direction, the whole thing is placed such that this outer wheel of the tandem axle is exactly at this longitudinal edge. Similar idea when you have a tridem axle. When you have a tridem axle, the front transverse is placed over here as usual. In the rear side, the first wheel of the tridem axle group, the first axle of the tridem axle group is placed again on the transverse joint within the same slab. So it's assumed that this distance is 4.5. And then the remaining two axles in the tridem axle group are placed on the slab which is behind it. Again, there are dowels over here, so some amount of load transfer is going to happen. So it's not going to be that these are not going to have any effect at all. They will have an effect. And then overall, the entire thing is placed such that this tridem axle wheel is exactly at the longitudinal edge. So this then is the critical loading condition. So this was the critical loading conditions for bottom up cracking. As you saw over here, for bottom up cracking, we don't take the front steering axle into account. For top down cracking, we do take the front steering axle into account. As you can imagine, in this particular configuration, then the top down cracking will be relatively less in magnitude. The stresses will be relatively smaller compared to bottom up cracking, because the front steering axle is not a particularly heavy axle. So, and we'll see that in our solved example also, that indeed in this kind of loading configuration with IRC 58 uses, the fatigue damage due to top down cracking is generally less than the fatigue damage due to bottom up cracking, because we use these front steering axles and they are significantly lighter than the remaining axles. Okay, so let's talk a little bit about how these stresses are calculated. So knowing what are the critical loading conditions. Now we know what the critical loading condition is. From our previous lecture, we also saw what is the temperature distribution, the recommended maximum temperature distribution values, although they tend to be a little bit very conservative, not a little bit, quite conservative. But nonetheless, if you want to use those values, so we know now what is our traffic input, we know where to put our critical loads, material properties we already know, and then we know what value of delta T to use to characterize climate. Now the question is, given all this, how do we finally calculate stresses? Because ultimately we need our mechanistic empirical analysis begins by calculating stresses. Alright, so here is clause 6.2.1. It's a very important clause in this, which explains how stresses are calculated. Let me just go through it because it nicely gives you a little bit of history also. Okay, since the loads causing failure of pavements is applied by single tandem and other axles, stresses should be determined for the conditions illustrated in those figures. So 3 to 6, these are the same figures basically, which I showed previously. So that means the stresses should be evaluated for these critical loading conditions. There was a software called IIT Rigid, which was developed in IRC, which was part of IRC 2002. So as I said, around the 2000s then, the IRC code, like the US code, started moving away from Westergaard's theory. And it started moving towards using finite element method, and the program which was used back then was IIT Rigid. IIT Rigid, by the way, was actually based on that general continuum model, which is why I pointed out, del dot sigma is equal to 0. It was based on this. So IIT Rigid software was used in IRC 2002 for the computation of flexural stresses on the edge due to single and tandem loads based on Pickett and Ray's work on computational stresses in infinite slabs. So here again, the assumption was that an infinite slab was made. So although in IRC 58, there was a movement away from using Westergaard's theory to using modern finite element methods, it was still based on analysis that considered infinite slabs. That is a problem. We already talked about even Westergaard's theory made the assumption of infinite slabs. Problem with that is you tend to significantly overestimate stresses. So the software is still valid for computational load and stresses in edge regions without any concrete shoulders and without any temperature gradient. However, it wasn't necessarily the most appropriate way to do it. Therefore, finite element method is most appropriate for computation for a variety of loads, and so a new software program was actually used in the current edition. So IRC 2015, but also its immediate predecessor edition. So the third revision and the fourth revision, there the stresses are actually calculated using a different program which was called IIT SLAP 2. Also, this was a software developed in IIT Kharagpur as well. It was to compute flexural stresses due to the combined action of loads and different temperature differentials. So this particular program, IIT SLAP 2, is developed. So for these load configurations as well as the temperature and for thickness and material properties, etc., IIT SLAP 2 was a new program which was based on the finite element method, which was used then to calculate stresses. Okay, what were the different cases which were considered for stresses. And this, by the way, can very neatly be also fitted in with those neural networks we talked about in MEPDG. I'll refer to that in a second. But if you look at what cases were analyzed, so the cases analyzed are as follows. These are again all for non-linear temperature distributions for bottom-up cracking. Pavement with tied concrete shoulder. So basically you had tied and untied. And I had mentioned this in an earlier lecture. The way IRC 58 writes it, if it's a tied shoulder, it writes it as tied concrete shoulder, which makes sense because you can only put the tie bars if you actually have concrete over there. You don't put the tie bars if you have a bituminous concrete over there. And if you have untied, then it simply calls it without concrete shoulders. So I generally find it's a little bit troublesome to say without concrete shoulders because that can mean with a bituminous concrete shoulder. Generally, I find tied and untied describes the physics or the behavior of the stresses much better than saying with and without concrete shoulders. But nonetheless, the terminology is tied concrete shoulders means tied and without concrete shoulders means untied. So one level of factorial is pavements with tied or untied concrete shoulders for a single rear axle and similarly tied and untied for a single tandem axle. It was found that the tridem axle creates only very small stresses, and so for bottom up cracking alone, again for non-linear temperature distribution for bottom up cracking, tridem axle is actually not used in the analysis, and we actually don't have a formula or any way to calculate it in IRC 58 in case we have tridem axles. Which means, by the way, in this particular figure which I shown before, in this figure which I shown before bottom up cracking, although this figure is shown over here with the tridem axle, this is actually not considered in the design. So we do not consider the tridem axle repetitions for bottom up cracking. It was found to be very small. I will add just my personal observation on this. I don't fully agree with this approach. I think it's necessary, even if it's a small stress, it's necessary to still consider it. Don't decrease the amount of stresses being considered. Try to be as accurate as possible. So that's my philosophical idea on it. Anyway, for top-down cracking, again for top-down cracking, that means when delta TL is less than 0, here only linear temperature distributions are used. So if you go back to the previous lecture where I had talked about how IRC 58 takes climatic conditions into account, I had mentioned one clause or one comment which they had over there, which said that for bottom-up cracking, you have a non-linear temperature distribution. For top-down cracking, the term used was nearly linear temperature distribution. So it's almost linear. I had mentioned that I somewhat disagree with that. That is correct, perhaps late at night, after midnight to maybe 6 a.m. That is correct. But earlier during the night, that is when you have the sun has just set and the pavement is starting to cool down. During that period, actually, you can have fairly non-linear temperature distributions. So I don't fully agree with this analysis, but nonetheless, to just go through what the analysis is. So for top-down cracking, it assumes only a linear temperature distribution. Here again, it was found that tridem creates a relatively small stress, but it is still considered. And in this case, the consideration is pavements with and without dowel bars. So again, when we're talking about tied shoulder or untied shoulder, we're talking about tie bars in the longitudinal direction. So it's these tie bars over here. But in this case, now over here, what we have, our loads are never placed. For bottom-up cracking, the load is never really placed at the transverse joint. So there is no explicit consideration for whether you have dowel bars or not. This also, I'll add, I somewhat disagree with this idea also. In my opinion, you should always consider dowel bars because some amount of load transfer does happen. Even if it's small, it should not be neglected. I don't think it's enough to actually neglect it. Nonetheless, for top-down cracking, because the load is placed at the transverse edge, there is explicit consideration of whether dowels are present or not present. Although I will say in practice, we almost, at least on highways, we almost always have dowels. So it's a little bit superfluous in my opinion to do this analysis. Almost always you do consider dowel bars. Anyway, for pavements with and without dowel bars, having front steering axle with single tires and first axle of the rear axle unit placed on the same panel as depicted in figure 6. So basically the same loading conditions as I showed over here, but with consideration for both doweled and undoweled sections. What has been found is tridem axle units has been considered for analysis in combination with the front axle. Although the stresses due to them tend to be small, they still have been considered. The front axle weight has been assumed to be 50% of the weight of one axle of the rear axle. So that means if we take one of the axles, so just as an example of the illustration, let's take this tandem axle case. Suppose it's been found that the weight of the tandem axle is maybe 200 kilonewtons. That means the weight of each individual axle in the tandem axle is going to be 100 kilonewtons. And the assumption which was made in the analysis, and this is, in my opinion, is a little bit of it's not unjustified analysis, but it's a little bit too big of an assumption to make. But this was the assumption which has been made in the code. The assumption being made here is that the front axle is 50% of the rear axle. That is going to be 50% of 100, 50 kilonewtons. This again, I do not agree that this is correct for the simple reason that the weight on the tandem axle depends on what loading has been put inside the truck. What are you carrying? Are you carrying steel? Are you carrying wool? Are you carrying clothes? Are you carrying furniture, etc.? Depending on that, the actual load is going to be different. Whereas the load of the steering axle is basically the engine, the driver, and the driver's personal effects and any other parts of the chassis. Those do not change. So I personally do not agree with the idea that the front axle weight should be a function of the rear axle weight. These two are more or less independent of each other. Nonetheless, sticking to just explaining what happened in IRC 58, so this was the assumption which was made. That it was assumed that the front axle weight or the steering axle weight is 50% of weight of one of the axles of the rear axle. So if it's a single axle in the rear axle, it's that 50% of that. If it's a tandem axle, then it's half the tandem axle and half of that. If it's a tridem axle, then it's 1/3 of the tridem and half of that. That gives you the weight of the front axle. That's the assumptions which are made over here. Okay. Furthermore, what they also add is, for heavy traffic conditions, dowel bars are usually provided across transverse joints. And I should say again, today as JPCP is constructed, almost always provide. We rarely ever don't provide dowel bars anymore. Tight concrete shoulders are also usually necessary for high volume roads. However, for traffic volumes less than 450 commercial vehicles per day, tight shoulders and dowel bars are generally not warranted. I'll say they're still used in practice. They're not warranted, they are used in practice. So what they found is the result of the finite element analysis has been used for computation of flexural stresses with and without dowel joints and tight concrete shoulders. So we have both those sort of cases. The terminal load transfer efficiency. So load transfer efficiency, we already defined what it is in earlier lectures. Terminal load transfer efficiency just says that at the end of the service life, after a fair amount of degradation has taken place, the terminal load transfer efficiency is taken to be 50% and 40% respectively. That is respectively for shoulders as well as transverse joints for computation, and this is found from MEPDG. The MEPDG actually recommends 60 and 50% for doweled and tight joints. So it is assumed that the load transfer for dowel joints in India is 50% and it's 40% for tight joints. So this is for dowel and this is for tight joints, and this is based on observations in the MEPDG guide that the terminal load transfer efficiency tends to be 60% and 50%. Now, one issue over here you see clearly is we are using the terminal values. The terminal values occur after 20, 30, 40 years. The terminal values are being used for the entire analysis period. So initially when the pavement is first constructed, the load transfer efficiency will actually be 90% or more. Over time, it will decrease to maybe 50% or 40%. But the assumption is that we just decrease the load transfer throughout from the entire time. It goes back to what I said earlier in the previous lecture, that the IRC 58 design is a very, very conservative design. It's conservative on the temperature side. We already talked about that. It's also conservative on the load transfer side. It's actually assuming that the load transfer is the worst case scenario. The worst load transfer which happens is assumed to happen right from the beginning instead of happening just near the end. It goes back to the issue that the IRC 58 is not really an incremental load analysis model. It's not doing an hourly or a monthly type of load analysis, incremental analysis. The analysis is meant to be done in one shot for the entire design period. And that's why, as of now, it's not possible to actually take into account the degradation of load transfer. Whereas the MEPDG, although I didn't talk about it in those lectures, it does actually have a model where the load transfer decreases over time. Because it's a truly incremental model, it does actually decrease the load transfer over time. Anyway, so as it says over here, this has been done to make the design more conservative considering overloading in India. Again, I'm not fully convinced that it had to be this conservative, that from 90% you bring it down to 50%. I'm not sure that sort of excessive conservatism was warranted. Anyway, one thing to keep in mind, one thing which was fixed was slab size was kept as 3.5 by 4.5 meters always in the analysis. In practice, we can sometimes have slabs which have slightly larger or slightly smaller than this. And in the MEPDG, there are actually ways to change the slab size as well, because that was one of the variables to the neural networks. But in IRC 58, this was the fixed slab size which was considered, 3.5 by 4.5. Okay. In terms of fatigue damage, so I haven't talked about yet how to calculate stress. I'll show you the equations to calculate stress, but setting that issue aside, once you calculate stress, then these equations are used for calculating fatigue damage. I've shown you this SN curve before, I'm not going to repeat it, but here again, keep in mind the 0.45 stress ratio, this I had called the endurance limit. So this will come up again in a couple of lectures, so just keep in mind, this is the endurance limit, 0.45. Okay. One thing about this fatigue damage function, what IRC 58 does not have is an explicit consideration of reliability. We had talked about the fact that reliability depends on the class of road and the type of road. And we saw in the MEPDG how reliability is incorporated statistically into the final prediction of distresses. In the IRC 58, there's no explicit consideration of reliability. There is actually an appendix. So this slide which I have over here, this is actually from an annexure. I forgot which annexure, maybe annexure 6, but it's actually from an annexure of IRC 58. Basically, what this said is that this particular equation roughly corresponds to a reliability of 90%. But they also suggest reliabilities for different type of roads, so 60% reliability for village roads and 90% for highways. This is in an annexure, and generally this formula is never used. In general, this formula is used, which corresponds to around 90% reliability. So in India, based on IRC 58, we are basically doing analysis for 90% reliability. Okay. Furthermore, I already pointed out previously, it was suggested in the code that for bottom-up cracking, the analysis should be done from 10 a.m. to 4 p.m. and then for top-down cracking, it should be done from midnight to 6 a.m. So the same thing is provided over here, that the cumulative fatigue damage for bottom-up and top-down cracking are to be calculated separately within 10 a.m. to 4 p.m. for bottom-up and then 0 a.m. to 6 a.m. for top-down. And this summation is to be done for all the load conditions. The delta T stays the same. So it's just to be done across all the load conditions, that is the different single axle, tandem axle, and tridem axle, and the number of repetitions that they have. So this cumulative fatigue damage is to be calculated based on bottom-up cracking and top-down cracking separately. And then what IRC 58 says as a design criteria is failure is said to occur when the total of the bottom-up and top-down fatigue cracking is less than or equal to 1. Which brings me to probably the biggest deviation between MEPDG and IRC 58. MEPDG, the E part as I talked about, is taking fatigue damage and using a transfer function, it's converting it into a distress. We do not have such functions. We do not have transfer functions in IRC 58. So in IRC 58 and also IRC 37, by the way, for flexible pavements, we do not actually calculate distress. We do not quantify the amount of cracking, the amount of faulting, the amount of punch outs, etc. Those are not quantified. Instead, our failure criteria is purely a mechanistic failure criteria that the total fatigue damage is less than 1. I had already mentioned to you why this can be a problem, why for an engineering perspective, it is not appropriate to use the fatigue damage concept because you can't actually measure it. And at least in my opinion, many problems come out due to this assumption. And probably the next edition of IRC 58 should really focus on updating this particular assumption. It's not a very good failure criteria to use. Anyway, that aside, another problem which I've marked over here is it simply adds up the fatigue cracking due to bottom up and top down. It says once you have total fatigue cracking for bottom but top down less than 1, that's when it's called failure. The issue here is this can lead to a little bit of double counting. Why is that? Because the same slab, the same pavement can have top down cracking as well as bottom up cracking. Because after all, top down cracking and bottom up cracking depends on a transient temperature condition. The same pavement during the day will experience bottom up cracking and during the night will experience top down cracking. You have to take into account that some slabs therefore have both top down and bottom cracking, and you should subtract out the intersection between the two. So purely adding CFD from bottom up and top down could lead to some amount of double cracking, which should not be considered. So that's one issue which I find in this particular one. Now, there is no companion software. Well, this thing which I'm putting over here, there is actually no companion software. So IRC 37, if any of you have taken the class on flexible pavement design, there is a companion software in IRC 37 which is called IIT Pave. And IIT Pave is a layered elastic analysis software that's used to calculate strains it can calculate anything, but it can calculate deflection strains and stresses, but mainly it is used to calculate strains in IRC 37. There is no such program, there is no such companion software provided by IRC 58. Instead, there's actually an Excel sheet which has been included. So if you buy the code, or if you go to a library which purchase the code, there's actually a CD which comes with it. The CD actually has an Excel sheet or a spreadsheet which actually does a lot of calculations. How can you run a finite element program using an Excel sheet? It's a good question. And the answer is that actually there are two methods. How do you calculate critical stresses in JPCP using IRC 58? It actually gives you two methods. Both the methods are based on the finite element analysis of IIT SLAB 2, but the program IIT SLAB 2 is not provided with the code. Instead, an Excel sheet is provided which has two methods to calculate. One is using charts. So the IRC code itself actually has a number of charts. So this can be also called a visual method. I'll show you an example in a second what those charts are. So there are actually a number of charts where you can just draw a line and calculate what is the, or just pull out, look up the chart and see what is the value of the critical stress. The other way, which is generally what has been implemented in that Excel sheet and which I also do recommend that you use, is using regression equations. So what they did is they ran IIT PAVE multiple times and then they created some regression equations out of it which can be calculated. Obviously, the regression equation is an approximation. You have some amount of R squared. This is not very different from what MEPDG does. MEPDG does, recall, they use they use ISLAB as the FEM program, but then they develop a neural network on top of it. The neural network can be considered a very large non-parametric regression. Instead of doing that, what IRC 58 does is they just created a lower order regression, a more parametric lower order regression. So both MEPDG as well as IRC 57 are using some type of surrogate modeling or some type of regression model to reduce the amount of computations and to avoid having to do a full-blown finite element analysis. So these regression equations, which I'll show in a second, these are what are basically to be used mainly. The visual charts are okay for valid for just checking your results, but the regression equations are what are to be used and have been implemented in the Excel file which comes along with the CD with IRC 58. Again, there is no companion software like IIT PAVE. Here is an example of a chart. There are actually many charts, but one example is stress due to single axle load, delta 80 kilonewtons, delta T is equal to 0, so you have a flat slab without concrete shoulder. If you look at it, on the x-axis you have slab thickness, on the y-axis you have this is the critical stress, although it says flexural stress, is the critical flexural stress. And then you have 4 lines for different K values for the subgrade. So if you know that you have 80 kilonewton single axle, if you know delta T is equal to 0, if you know you have an untied shoulder, then if you have a 300 mm thick slab and you know the K value, then you draw a line like this and you get the critical flexural stress. Here is another one. Similarly, there are actually 111 such figures. So a bulk of the IRC 50 is actually quite a thick code. A bulk of it is a number of these figures which are contained, I think, in Annexure 7 or in Annexure 8. Similarly, there are these type of equations which are also provided. So these are the regression equations which are coded up. So here, depending on the K value which is being used, different equations are provided to calculate S. S here refers to the critical stress. It's in megapascals. And you see here, you've got a number of different values. I'm not going to talk too much about these equations because in the next lecture, I'll actually take you through solving one of these equations. So because they're relatively simple closed form regression equations, they can actually be calculated by hand, although in practice, you should use the Excel sheets provided for it, but they can be calculated by hand. So when you have single axle, this is for bottom up cracking, by the way. When you have single axle pavement with tight concrete shoulders, you have these 3 equations. When you have without tight concrete shoulders, you have untied shoulders, then you can have these sort of, you have additional equations like this. And for top down, you similarly have an additional equation. There are a number of terms over here. I will explain and define these terms in the next lecture. So here I just wanted to show you that these equations exist. I didn't want to fully define this as it is. It's a little bit premature for that. There is some important considerations, however. These regression equations are dimensional. That means that every input actually has a unit. As a simple example to illustrate the point, here we are trying to calculate stress. The stress is in megapascal. Here we have delta T as an input. This is in degrees Celsius. So that means this coefficient over here actually has the units of a very odd unit of megapascal per degree Celsius. So these equations have not been non-dimensionalized, and that can be somewhat concerning because in that case you can make an error depending on your choice of units. Generally, I had said previously, you should be unit consistent. In this case, you actually have to use the exact units recommended. So the regression equations are dimensional. Check the units of each input. In particular, the unit choice is also a little bit odd. Loads are shown in kilonewtons. The K value is shown in megapascals per meter, which in another way can be written as Newton per mm square meter. Somewhat odd way of writing it, or maybe one way to write it is this could be kilonewton per meter square mm or something. So you get some odd combinations of units in this case. So it's not dimensionally consistent. You have to be very careful to choose the correct units for whatever input you're using and use the exact same units recommended by these regression equations, or your answer will be wrong. So it's very much unit dependent. Generally not a good way to develop regression equations. So I hope a future edition of IRC 58 will try to non-dimensionalize these values so that it becomes unit independent. Also, you want to note that delta T. So we saw that for top-down cracking, we had delta T value. For bottom-up cracking, there's a delta T, which is a recommended input. We talked in the previous lecture on where to get these inputs from. That's from that table 1 in IRC 58. Note that it is an absolute value. So top-down cracking occurs when delta TL is less than 0. But the input you should be using should be the absolute value. Do not use a negative value. Very common mistake I've seen, that because it's top-down cracking, students apply a negative value over here. Nothing wrong with it, but that's not how these regression equations were developed. The regression equations were developed with the assumption that delta T was the absolute value. I do not agree with this approach. I think this should not have been done because it leads to confusion, but I'm just telling you this is what we used. One piece of thought which I think is a very important issue is the input is delta T. I had mentioned in the previous lecture, for the same nonlinear temperature distribution, I can get you this for two different nonlinear temperature distributions. I can get you the same equivalent linear temperature difference, but the nonlinear component of the temperature is going to be different for both. The nonlinear component is going to generate eigenstresses. Can we truly predict the eigenstresses, which are a nonlinear component, with only a linear temperature input? I don't think, from a mathematical perspective, that doesn't seem correct. So the input is only the linear temperature value. And from that, we also want to calculate the eigenstresses, which are nonlinear. I don't think that's fully correct, but to check that, and again, this is the last thing on today's lecture, we did a little bit work during one of my students' research also, where we actually did a number of checks where we looked at nonlinear temperature distributions, and we tried to then calculate the stresses separately for bottom up and top down. So we tried to calculate stresses over here. This was ratios. This is a stress ratio. We calculated the total stresses and divided by the flexural strength using both ISLAB. So this finite element model was ISLAB, which has explicit consideration of eigenstresses. So we definitely know how ISLAB calculates eigenstresses, and we use these equations which I just showed from IRC 58. And this is what we got. What we generally found, again, going with the general theme, that if these are the stresses which are calculated from the ISLAB, and these are the stresses which are calculated from IRC 58, we saw that the IRC 58 stresses are higher. So these stresses which are being calculated using these equations over here, and this, by the way, is total stress. So eigenstress is built into this. What we conclude from this is the IRC equations, they are considering eigenstresses indirectly. There is some sort of indirect, it's actually built in, because delta T cannot tell you anything about the eigenstress. That means this 0.1089 or the 0.0297, somehow the eigenstress information is encoded empirically into these empirical coefficients. I don't think that's a good way to do it. It would be better if a proper decomposition was done. But what we see is, at the end of the day, these stresses as predicted by IRC 58 tend to be on the higher side. That there's somewhat of an over prediction which is happening, or a conservative design which is happening, which goes on with the general thing we've been talking about so far, that IRC 58 is a very, very conservative sort of code. The stresses which are ultimately predicted tend to be quite high, and all the other inputs also tend to be relatively high. So your delta T values tend to be a relatively higher side. The way you're accounting for the load configurations and the traffic distribution, that also tends to be conservative, and your stress calculations are also conservative. It's a very, very conservative way to do the design. I'm not sure it was strictly this necessary to be that conservative. Anyway, that's overall how this works. So it appears to be very conservative. It's not that surprising. The code actually says in many places that it is a very conservative design. Particularly, I'll say, for those of you who are doing research, who want to do any research inside this field, you have to understand that in design, that is in practical matters, maybe you can be very conservative. That depends on the legal regime the country is following. So maybe you can be very conservative. But when you're doing design, you can't afford to be this conservative. So when you're doing research, you can't afford to be this conservative. In research, we value accuracy over conservativeness. So these equations may be fine for design. If you're trying to use them for research, you have to be very careful and understand that they're very, very conservative, and your results also are probably very conservative, which can cause problems if you're trying to publish any work in any reputed journals. Anyway, so I showed you these equations. You can see there's quite a lot in the equations, and particularly because of the issue of units, a lot of ifs and buts comes into these considerations. So in the next lecture, I actually want to show you how to solve some problems using these equations, so you have some amount of understanding of these, keeping in mind that you should in general always use the Excel sheets provided. But if you need to develop the sheets on your own, or if you need to solve it by hand, maybe in an exam, I wanted to give you a couple of examples of how you can do that. So we will do that in the next lecture, where we will look at IRCP 58 design of JPCP. It's part 1, where we'll just looking at these stress calculation equations. Thank you.